Good morning. Today we're going over our first lecture for solutions and solubility. And our first problem here is looking at the solubility of some solute X in water at two different temperatures. This problem is looking not just is something soluble or not soluble, it's saying how soluble, can we quantify that? Can we do math with that and describe what's going on here? And that's what this little table is saying. This table is saying, look, at 20 degrees Celsius, I can fit 11 grams of X in 100 grams of water. This becomes a new conversion factor. For a saturated solution, 100 grams of water contains 11 grams of X. And at 30 degrees Celsius, I can fit 23 grams of X into 100 grams of water. Okay, interesting. And here now we've got a saturated solution of X at 20 degrees Celsius, so under these conditions. And I'm only using 35 grams of water. No big deal. 35 grams of water. Dimensional analysis tells me that every 100 grams of water can contain up to 11 grams of X. If I just use dimensional analysis, I can calculate the number of grams of X that can be dissolved in only 35 grams of water. So 35 times 11 divided by 100 gives me 3.85 grams of X in my saturated solution. So the question they're asking then is how much more solute can be dissolved if the temperature is increased to 30 degrees Celsius? Well, under these conditions, we can see that 35 grams of water could dissolve up to 23 grams of X in every 100 grams of water. And that comes out to 8.05 grams of X. This is how much can be dissolved in my 30 degrees Celsius water. This is how much is dissolved in my 20 degrees Celsius water. The question is not how much can I dissolve in 30 degrees Celsius, which would be 8.05, but how much more could be dissolved. So if I can get up to 8.05 grams, but I started with only 3.85 grams in there, then I subtract one from the other and see that I can add 4.2 grams of X to that water. All right, this next question is looking at solubility from the perspective of what kinds of things are going to dissolve what other kinds of things. And for the purposes of this one, what we're looking at is polarity and intermolecular forces. And we find that molecules which are polar will dissolve other polar or ionic, that is charged, things. And molecules which are nonpolar will only dissolve nonpolar things, or primarily dissolve nonpolar things. So we just have to look at these things and say, are they similar? Do we have two polar things, or one polar and one ionic? Do I have two nonpolar things? Those would be soluble or miscible, which means soluble at all proportions. And something which would be polar and nonpolar, if I put those two things together, those would not be likely to be miscible. So looking at these first two, H2SO4 and H2O, if we draw the structure for H2SO4, looks like this. So we have hydrogen bonding. And the structure for water, which has OH bonds. So both of these have hydrogen bonds. Both of those are highly polar. Those would be miscible, yes. Na3PO4, sodium is a metal and phosphate is a polyatomic ion. So this is an ionic compound. Water is highly polar. Polar and ionic things will go together happily. Here I have C8H18 and C6H6. And what we see with these is you only have carbon-carbon and carbon-hydrogen bonds, and neither of those bonds are polar because the difference in electronegativity between those two carbon bonds would be 0. Difference between carbon and hydrogen is 0.4. Neither of those is high enough to be on the polar threshold. So anything with just carbon and hydrogen atoms is going to be nonpolar. C6H6 is in the exact same boat, also only has carbon and hydrogen bonds, it also would only be nonpolar. So those are likely to be miscible. And the last two we've got here, CS2. CS2 looks like this, and it does not have polar bonds because the carbon-sulfur bond is not a polar bond. And CCl4, I'm going to draw this in its correct geometric shape. The CCl bond is polar, it's a polar bond, but altogether, when you add up all of these polar bonds, you find that the molecule is not polar because they all cancel out. So hopefully you guys remember this from our section on covalent compounds and molecular polarity. In order to get these right, you do sometimes have to start with the Lewis dot structure, move from there to the Vesper shape, then look at individual bond polarities and add that up to overall molecular polarity to see, as in this case, for instance, that this is a nonpolar molecule because it does not have polar bonds, and this is a nonpolar molecule because even though it has polar bonds, they all cancel. There's not a polar two poles, there's not two poles to that molecule. So all of those pairs would be miscible. You may have different pairs, so you may have to go back and review that section on bonds and molecular polarity and intermolecular forces. All right. In general, the solubility of something in water decreases as temperature increases. Now, usually solubility increases as temperature increases, as it was the first problem that we looked at. We saw temperature increased, solubility increased. That's true for most solid solutes. Like, for instance, sugar, salt would fall into that category. And also true of liquids, but gases, because they have so much kinetic energy, and would love to escape from that solution. Increasing the temperature increases the kinetic energy, does not help them stay in solution. So in general, the solubility of gases in water decreases as the temperature increases. Next, we've got units of concentration, and molarity is the unit of concentration that we're going to use all the time in this class from here on out. So for the rest of this chapter, for the rest of chapters on acids and bases, you're going to see it again as chemists. So you need to know what molarity is. So molarity is always given by capital M, but capital M isn't that useful. What is useful is what it represents, which is moles per liter. So capital M, which stands for molarity, is really moles of solute per liters of solution. If you can remember this, then you can use dimensional analysis to solve any molarity problem I hand to you. So for instance, here we're asked, what is the molarity of a salt solution if I have 29.2 grams of NaCl in 100 milliliters of water? Okay, since I was given grams, I need to convert to moles. Since I was given milliliters, I need to convert to liters, and then I could just put the moles over the liters and I will have molarity. So that's going to look like this: 29.2 grams NaCl. The molar mass of NaCl, let me pull up my periodic table. And let's zoom in a little bit here. NaCl has 1 chlorine at 35.45 and 1 sodium at 22.99 for a total mass of 58.44 grams per mole. So that gives me moles. Now I can say 100 milliliters of water and 1,000 milliliters of water, or in every 1 liter of water. That's going to give me 0.1 liters water. And I can, oh, I didn't plug this in, did I? 0.49965. So if I have moles and I have liters, I just take the moles, divide by the liters, and I get a molarity of about 5 molar. So 5 molar. All right, so now what is the molarity of each of these solutions? Each of these is exactly the same story because I'm given grams and I'm given milliliters. So I'm going to take grams and convert to moles, and take milliliters and convert to liters, and then divide moles by the liters because that's the unit of molarity. So let's try that here. NaHCO3, Na was 22.99, hydrogen 1.008, carbon 12.01, and oxygen 3 times 16, 84.008 grams per mole. So 30.5 grams NaHCO3, 84.008 grams NaHCO3, and 1 mole NaHCO3. And now I've got 310 milliliters of solution. I actually don't have to calculate that separately. I could just keep going on this line. 310 milliliters and 1,000 milliliters in 1 liter. And that lets me cancel out milliliters. And now I'm left with units of moles per liter. So 30.5 divided by 84.008 divided by 310 multiplied by 1,000 gives me molarity of 1.17. Next we have H2SO4, that's 2 hydrogens plus a sulfur. Let's see here. Sulfur is 32.07 plus 4 oxygens gives me a molar mass of 98.086 grams per mole. So we can say 54 grams H2SO4, 98.086 grams H2SO4 in 1 mole H2SO4. Grams cancel. And then we're in 250 milliliters of solution. Another thing is if you can eyeball that and appropriately designate that that's 0.250 liters, you could do that. If not, you can take it stepwise like this. But that gets me moles per liter, and I can plug this in. 54 divided by 98.086 divided by 0.250 gives me 2.2 molar. And finally, 15 grams of NaCl. And I forget the molar mass that we calculated there. 22.99 for the sodium, 35.45 for the chlorine. There we go. 58.44 for sodium chloride. And if we're at a 580 milliliter solution, that's 0.580 liters. Grams cancel, we're left with moles per liter, so 15 divided by 58.44 divided by 0.580 is 0.44 Here we go. Now these ones are going backwards. If I'm given molarity and I'm given volume, can I calculate moles? Well, yes, if I remember that molarity is moles per liter, I can use this to solve for moles. And I could either go forward or backward, but I'm going to go backward. What I call backwards is saying I'm going to start with the units they want and try to eliminate everything else, okay? I could do it either direction. But in this case, I'm going to start with recognizing that I have 0.31 capital M, which means moles per liter of the acetic acid solution. All right, notice how I didn't put down capital M because capital M is not useful. Moles and liters is because I need to do dimensional analysis. So if I start here, I put that front and center, then I know I need moles. I just have to get rid of liters. I have 0.160 liters. I set that up. I can cancel liters and I'll be left with moles. Dimensional analysis tells me what I have to do here. I could have memorized, for instance, that if I multiply the molarity by the number of liters that I get the moles, but that's too much trouble. I don't need to have to remember that. I don't need to remember that. All I have to remember is that molarity is moles per liter, and then depending on what units I want where, I can just write it down in the right place so I get the units and therefore the answer I want. All right, next, same story. If I have 0.28 molar sodium hydroxide, that means I have 0.28 moles sodium hydroxide in every 1 liter of that sodium hydroxide solution. And I have 2.10 liters of my sodium hydroxide solution. So multiply those through, liters cancels. That's 0.588 moles. And finally, if I have 2.7 moles per liter of my nitric acid solution, and I have, in this case, 0.920 liters of that nitric acid solution, calculate that I have 2.48 moles of nitric acid in that solution. Now that's going backwards because I started with the units that I needed, moles, and I went to eliminate anything else. The other thing you could do is start with something else you're given, like in this case, 920 milliliters. And then you might say, how do I get away from milliliters? Well, I know that molarity uses liters, so I'd better switch that. And then you'd say this is moles per liter, so in order to cancel liters, I would do 2.7 moles in 1 liter. And that gets me to moles. So that's going, as I say, forwards as opposed to backwards. The only potential downside is that sometimes when you work your way forwards this way, you might end up with the units you want on the bottom. In this case, that didn't happen, but sometimes it does. So it doesn't hurt to kind of try it from both directions. All right, this next question is asking how many milliliters of a 0.750 molar HCl solution do you need to obtain 0.0041 moles of HCl, and milliliters is a unit of volume. And you note here I've got 0.75 moles HCl in every 1 liter of HCl solution. So if I want milliliters, then I better put my volume. If I want volume, I'm going to put this on top. 1 liter of HCl, 0.75 moles HCl, and 1 liter of anything contains 1,000 milliliters. So now I've got milliliters, but I need to get rid of moles. There they gave me moles. Moles of HCl cancel, and I'm left with milliliters of that HCl solution. So 1 divided by 0.75, multiply that by 1,000, multiply that by 0.0041, and I get 5.47. All right, next, all of the water in the solution evaporated and this much NaCl was obtained. What was the original volume of the sample? Okay, so we had a 0.200 moles per liter solution of NaCl. And in the end, we also had 0.150 moles. And we wanted to know what was the volume. And this is, of course, these are all given in milliliters. So again, we're going to be solving for volume. So I'm going to put volume on top here. Just going to flip that. And I can eliminate moles by putting that in there. Moles of NaCl cancel. And then we're going to have to remember that 1 liter has 1,000 milliliters. So liters cancel. Plug that in and I get 750 milliliters. All right. Next, what we're doing is we're going to put together what we've been calculating with moles per liter and molarity with what we have done previously on mole-to-mole and mole-to-mass conversions. So pulling out your conversions roadmap and do a little bit of off-roading with the concentration. But other than that, we're going to do what we can to get on track here and answer the question. So they want to know how many grams of NaHCO3, so this thing, how many grams of this would I need to put on the spill to neutralize this many milliliters of this concentration of H2SO4. So we're going from NaHCO3, which is one thing, to H2SO4, which is another thing, or vice versa. We're starting with H2SO4 and going to NaHCO3. So if I pull up my conversions roadmap here, I see that I can get to grams of something different from what I started with by going through the moles of something different. If I start with the moles of the thing I start with. And we've done that from grams, but now we have to start with concentration. I can use concentration to solve for moles of A, and from there go to moles of B, and from there go to grams of B. So what I'm doing is kind of off-roading from moles of A using the solution concentration units here to get to moles of A. Like we did with gases, you could use PV equals nRT to go from moles to pressure, volume, or temperature. So starting here, what I have is 0.75 moles H2SO4 in every 1 liter of that H2SO4 solution. And note, never at any time have I put a capital M here because that's not what's needed for dimensional analysis. Again, I just instantly convert that to moles per liter. And if I have 0.480 liters of that, then liters of H2SO4 can cancel, and I'm left with moles of H2SO4. Awesome. Now I'm on the roadmap. I'm at moles of A, and I can get to grams of something else, grams of B, by following the roadmap here. So the coefficients between H2SO4 and NaHCO3 are right there. 1 mole H2SO4 for every 2 moles NaHCO3. And once I get to moles of NaHCO3, I can go to grams if I can calculate the molar mass. So sodium was 22.99, one hydrogen is 1.008, carbon 12.01, and 3 oxygens at 16 each gives me 84.008 grams per mole. And that's going to go on top. Moles of NaHCO3 cancel. Now I can plug this all in. We've got 0.75 moles per liter of H2SO4. Multiply that by 0.480 liters of H2SO4. Multiply that by 2 moles of sodium hydrogen carbonate for every 1 mole of H2SO4. And multiply that by 84.008 grams of NaHCO3 in 1 mole of NaHCO3. And I get 60.49 grams, or 60.5. This is the same kind of story, but instead of starting with molarity and going to grams, I'm going to start with grams and then move towards molarity and then use that to solve for milliliters. Okay, so if I'm looking at my roadmap, I might say I'm going to start with grams of A. We'll make silver bromide A. I could use the molar mass to determine the moles of silver bromide and the coefficients to determine the moles of my Na2S2O3. Once I know the moles of the Na2S2O3, I can use the number of moles per liter to determine how many milliliters that is. So it goes like this: 0.720 grams silver bromide. Silver is 107.9. Bromide 79.9. So we've got 187.8 grams per mole. Now, according to this balanced equation, 1 mole of AgBr reacts with 2 moles of that Na2S2O3. And that I recognize that capital M means moles per liter, and I need moles on the bottom in order for those to cancel. So that's going to be 0.0130 moles Na2S2O3 in 1 liter of that solution. So my moles cancel here. And they asked for milliliters, so I'm going to take that one more step here. 1 liter of anything, 1,000 milliliters. My liters cancel. So 0.720 grams of silver bromide divided by 187.8 grams of silver bromide per mole, multiplied by 2 moles of Na2S2O3 for every 1 mole of silver bromide, divided by 0.0130 moles of that Na2S2O3 in 1 liter of solution, and multiplied by 1,000 milliliters for every 1 liter of solution, gives me 590 milliliters. All right, so looking at this again, by the way, just note these first 3 steps are things that you've already done, you've already been tested on, you should feel pretty good about. We're just putting the moles together with the molarity here in order to make that work. Okay, percent concentration is a different unit of solution concentration. And what we're doing here is looking at the relative amount of solute per solvent in terms of weight or mass. And it'll always be grams or milliliters, always grams or milliliters. So both of these are in grams, that works. Milliliters also works. And the reason that it's grams or milliliters is because in water, which is your presumed solvent, 1 gram is equal to 1 milliliter. So you can use those kind of interchangeably. But it's always amount of solute divided by solution multiplied by 100 to make it a percent. So in this case, if I've got 46.6 grams of sodium hydroxide, that's my solute, divided by the solution, which contains both the solute and the solvent. So that is 46.6 grams plus 245 grams. That's the total mass of the solution. Then we're going to multiply that by 100%. So 46.6 divided by 46.6 plus 245, which gives me a total mass of 291.6. And then we're going to multiply that by 100 to see that we've got here a 15.98% solution. We're about a 16% solution of sodium hydroxide in water. Next, we're looking at the mass of volume percent. That's telling us that MV tells us we're going to use grams for the top and volume for the bottom. So if we're using grams for the top, we see that we have 158 grams of NaCl. And on the bottom, the volume is 2.21 liters. And I told you we have to use milliliters. So 2.21 liters at 1,000 milliliters per liter, that's going to give me 2,210 milliliters of our solution. So this is a mass over volume. So 158 divided by 2210, that gives me the fraction. Multiply that by 100 to make it a percent. This is a 7.15% mass per volume solution. Your numbers are almost certainly different from my numbers, so don't just put in 7.15%. But that's how to do that one. All right, so these problems are asking us to go backwards, essentially. That is, instead of calculating weight percent, if I know that, then calculate volume or calculate my mass. And that's easy if you know the formula. It's always going to be, in this case, since it's weight per volume, it's going to be X grams of solute in Y milliliters solution equals, multiply that by 100 to make it a percent. That equals my percentage. So I can plug this in here and say, for instance, for this first solution, they want to know the number of grams. So X grams of solute in 52 milliliters of solution multiplied by 100% gave me a percent concentration of 6.5%. If I solve for X, I just need to divide both sides by 100%. To get rid of that, that gets rid of my percentage. And then multiply both sides by, sorry, that's an X, that should be a multiply. Multiply both sides by 52 milliliters. And that'll cancel. So what we get here is 6.5% divided by 100 gives me a fraction of 0.065. Multiply that by 52 gives me 3.38 grams of solute. Next, same story, they gave me volume and percentage. So I'm just going to plug that in here. I'm going to say 8.5% divided by 100. That gives me a fraction of 0.085. Multiply that by 300 milliliters of the solution. That's a 25.5 gram solution. Exactly the same thing. Solve for x, but in this case, I change this value to 300, and I change that value to 8.5%. All right, in this case, I'm asked to use weight percent to calculate volume instead of mass. So here I calculated mass. Now I'm going to set this up to solve for volume. And we see if I've got 1.5 milligrams over y milliliters of solution, multiply that by 100%. To get a 0.40% solution, solve for y in this case. What I'm going to do is multiply both sides by y, so that those will cancel, and this gets to be on top, and divide both sides by 0.40%. So now y milliliters is on top and it's by itself. I can plug this in and get 1.5 milligrams multiplied by 100% divided by 0.4% gives me a 375 milliliter solution. They did ask for two significant figures. Nope. Oh, I'm sorry. I should have known better. I told you specifically at the outset that you need grams here and not milligrams, and I neglected to convert. So 1.5 milligrams at 1,000 milligrams in 1 gram, that's going to be 0.0015 grams. So that gives us grams and milliliters. Let's try that again. 0.0015 grams multiplied by 100% divided by 0.4% gives me 0.375 or 0.38 milliliters. There we go. Here we go. Person with a blood alcohol volume, 0.08%. This is a volume per volume because alcohol is a liquid, and so it's more convenient to express this percentage as a ratio of volumes and not mass. But in this case, we're going to use milliliters because it's always grams or milliliters. So what volume of total alcohol does this represent? Assuming a blood volume, that's the total solution of 6 liters. So again, they want to know X milliliters of solute, in this case alcohol, in 6 liters of solution, which is 6,000 milliliters of blood. Multiply that by 100%, gives me 0.080%. I just set up the equation for finding the percent and I solve for x. So to solve for x, we're going to divide both sides by 100%. So cancel and multiply both sides by 6,000 milliliters. And we see 0.08 divided by 100 multiplied by 6,000. It only takes 4.8 milliliters of alcohol to put me at the legally drunk limit. Concentration in parts per million is almost exactly like the concentration in percentage. Concentration in percentage is mass or volume of the solute divided by mass or volume of the solution. Doesn't matter so long as you're using grams and milliliters, so they're comparable. Solution. And then instead of multiplying it by 100% to make it a percent, I can multiply it by 1,000,000 to make it parts per million, or I can even multiply it by 1,000,000,000 to make it parts per billion, or I could even multiply it by 1,000,000,000,000 to make it parts per trillion. In this case, they want parts per million, so that's going to be 10 to the 6. That's 1,000,000. That gives me my answer in parts per million. So this is the equation we're using instead, where this first part is the same as it was when we did percentages. So if I have 32 milligrams of sodium fluoride for every 20 kilograms of solution. Remember, we always have to use grams and milliliters. We always have to use comparable units. These are comparable because water is 1 gram per milliliter. So 32 milligrams of sodium fluoride would be 0.032 grams sodium fluoride. And 20 kilograms of solution is 20,000 grams of solution. I have to multiply that by 10 to the 6 to make it a parts per million. So 0.032 divided by 20,000. You can see why we use something like parts per million or parts per billion when you have a very tiny concentration. So 1 times 10 to the 6th, that gets me 1.6 parts per million. Now we've got parts per billion. To do that, we just multiply it by 10 to the 9th to get parts per billion instead of 10 to the 6th. So here we go. Just to remind, amount of solute divided by solution times 10 to the 6th, to the 9th equals parts per billion. And these amounts have to be milliliters or grams, both the top and the bottom. So we've got maximum concentration in the EPA for lead is 15 parts per billion. So 15 parts per billion equals 10 to the 9th multiplied by concentration here. That is the amount of solute divided by solution. And they're looking at, they want milligrams per liter. But if I do this, I've got to be grams or milliliters. So that would be grams, and that would be milliliters. So let's just solve for grams per milliliter. 15 divided by 1 times 10 to the 9th gets me 1.5 times 10 to the minus 8th. So what I have here, say 1.5 times 10 to the minus 8th grams of, in this case, lead in every 1 milliliter of solution or water. They want that in milligrams per liter, so 1 gram is 1,000 milligrams. Grams cancel, and there are 1,000 milliliters in 1 liter, so milliliters cancel, and now we're left with milligrams per liter. So 1.5 times 10 to the minus 8th multiplied by 1,000 milligrams in a gram multiplied by 1,000 milliliters in a liter, and I get 0.015 milligrams in a liter. Part B asks how many liters of water that's contaminated at that level would I have to drink in order to consume 1 microgram of lead. So starting with 1 microgram, and here I've got units of milligrams, and I don't know how to go from micrograms to milligrams, or I didn't bother to memorize that, but I do know that 1 microgram is 1 times 10 to the negative 6th grams. And I do know that 1 milligram is 1 times 10 to the negative 3 grams. And now I can plug in what I calculated here, now that I've gotten to milligrams, that I have 0.015 milligrams in every 1 liter of solution. Milligrams cancels, and I'll see what volume of solution I would have to drink in order to get a microgram of lead. So we have 1 microgram multiplied by 1 times 10 to the negative 6th divided by 1 times 10 to the negative 3 divided by 0.015. And I would have to drink 0.067 liters in order to ingest 1 microgram of lead. All right, last problem, multiple choice. And again, this is the format you're going to see on the exam. What we've got: calculate concentration in parts per million of a solution that has been measured at 450 milligrams per 150 kilograms of sample. I have to convert to grams, and I have to convert to grams. So 450 milligrams at 1,000 milligrams per gram gives me 0.450 grams of solute. 150 kilograms at 1,000 grams in a kilogram gives me 150,000 grams. And then we can just say 0.450 grams on top for my solute, 150,000 grams on bottom for the total solution. And because they want parts per million, I just multiply it by 1,000,000. And that will give me a concentration of 3 parts per million. There we go. That's it for this homework assignment. I hope that was helpful. Have a lovely day.